In this question, we're asked to find the volume of the solid obtained by rotating the region bounded by y equals the arctan of x, y equals 0, and x equals 1, and we're going to rotate that about the y-axis. So it's a volume question. Standard procedure is to draw the graph. So arctan and y equals 0 is the x-axis, and x equals 1 is that vertical line there, and I have the y-axis dashed in green. Okay. Y equals arctan does reach a horizontal asymptote at pi over 2. That's above 1. The part we need is right here. So I like to draw a second graph and decide which method to choose. And so on the first graph, I draw a rectangle that is perpendicular to the axis of rotation. And on the second graph, I draw a rectangle that is parallel to the axis of rotation. The perpendicular one is either disk or washer, but because of this gap that's between the region and the axis, then it's going to be washer. It's going to be in y because the rectangle is horizontal. It's going to be moved upward. The one that's parallel is always shell, no doubt about it, no question there. And then since it's upright for the rectangle, it's going to be an x. Okay, great. We'll set them both up, and then we'll choose one method over the other. Actually, we'll end up doing them both. Don't worry. Let's go to set up the washer. So what are you looking for in washer? In washer, you need to find, and the formula for it is you got to take the outside radius and square it, take the inside radius and square it, and then integrate that with respect to y in this case. So what would be the outside radius? The way you get the outside radius is you draw a line that goes from the axis through to the end of the rectangle. And so that orange distance there is to denote the outside radius. And that won't change as the rectangle moves upward. The outside radius will always be to that vertical line, and that's x equals 1. That distance there is 1. And so 1 is your outside radius. Next up is the inside radius, and you draw a line that goes from your axis just up to the rectangle for the inside radius. And that there is the distance off of the y-axis. We know that to be x. And so the issue is that as that rectangle moves upward, it's going to stay as the distance to the function y equals arctan, but the issue is that we need it as x equals. It's our job to solve for x, which normally is a difficult thing to do here, but in this case, to undo the arctan, to get inside, to get the x, you just take the tan of both sides. You tan the left, you'll tan the right. The tan of y would then be the tan of the arctan, and those guys would cancel of x. You just get x. So x is equal to the tangent of y, and that will be our inside radius. All right. And then what are we supposed to do with this? Well, we take this, and then we have to figure out the bounds, the lower bound and the upper bound. I call C the lower bound, and this is going to start at the region's bottom point, so that's going to be at 0. And then we're going to move it upward. We're going to move it upward until it's where 1, the vertical line, intersects the arctan. If x is 1 and y is the arctan of x, the intersection would be at the arctan of 1. What angle do you plug in a tangent, have it spit out a 1? The answer, pi over 4. So that's where we're going to stop at, pi over 4. And then we just plug in the players. We'll come back and revisit this later. Let's go set up the shell. For shell, what we do is attach the axis to the rectangle to get the radius. And how tall the rectangle is, that's the height. And there's the formula. So the radius is this orange distance here. Once again, this is distance off the y-axis, which we just call x. And it's okay to leave it as an x here because our integral is in x. And so the radius is x. And then the height is the function height, arctan of x. What about bounds? Well, you're going to start at 0. You're going to end at 1. Pretty straightforward for these guys. And then we'll plug them into the formula. Now, at first glance, looks like it's a fair trade. Either one is doable. We're going to find out that doing it by shell works. Okay, we're going to find out it's going to require integration by parts, and doing it by washer doesn't. At first, you think, well, how am I going to integrate tan squared? But it's not that bad. Let me do it the shell method for you first. At the very end, I'll just talk you through, and we'll quickly go through the washer method. Okay, great. So we have to integrate x times the arctan of x, and we can do that with integration by parts. I'm going to choose u according to the hierarchy. There's no log present, but there's an inverse trig. So u must be arctan. Normally, whether u be x, but we have terms now that are higher up in the hierarchy, u has to be those guys. If u is the arctan of x, that leaves everything else to be dv. So dv is x dx. What are we going to do with this? Well, we're going to have to integrate u and dv and take the derivative of u. Why are we doing that? We take the derivative of u so we can get du. We take the integral of dv so we can get v. These are the parts that are in the integration by parts formula. Okay, well, what is the derivative of arctan? 1 over 1 plus x squared, or 1 over x squared plus 1 if you write it that way. All right, so then what about the antiderivative of x? It would seem like you're getting worse. You're going up an exponent. It's x squared over 2. Put the pieces of the puzzle together. Our job is to do uv minus integral of v du. So u times v is x squared over 2 times arctan of x. And then minus the integral of v du. Let me just first write them next to each other, multiply. And then I'm going to basically pull out a half and put the x squared in the numerator. It's my new integral in blue there. It's supposed to be better. It's in a better place, supposedly. I mean, this is an integral we can do, but it's going to take some work, though. So let's go to the next slide and discuss how to finish this question off. And notice what I have here done with the integral is I'm treating it as an indefinite. I know it's a definite integral. We're going to plug in the bounds. I like to go all the way through to the antiderivative and then plug in the bounds at the end. Here we go. So this integral here actually is a polynomial divided by another polynomial, and the degree is of the numerator is equal to the degree of the denominator. This can be simplified whenever the degree of the numerator is more than or equal to the degree of the denominator. You can get simplification by doing the algebraic technique of long division. Divide the bottom into the top. You can do it. What you do is focus on the leading terms. You have an x squared, you want to turn into an x squared. All you need to do, multiply by 1. Put that above, distribute across the outside, put those down underneath, but subtract them. Use parentheses so you can recognize that the minus goes to both of them, and what's left over here is your remainder. You know you have your remainder when you get the result to be less in power than what you're dividing by. And so what this says to us, like normal, is you'll have the result, the numerator will end up being the, you'll write a fraction basically. The remainder is the numerator, and you'll divide by what you're dividing by here, x squared plus 1. So we get the 1, and then we get plus a negative 1 on top of x squared plus 1. It's a rewrite to our function that we're integrating. It's a better rewrite. It's better than it was, because these two terms that we now have as replacements are each terms that we can integrate pretty easily. We just have to sweat through that algebra. So here we are with our new integral, and we're going to integrate 1 and get an x. And what is this integral of 1 over x squared plus 1? It's the arctan of x. And there's a minus, so we just put a minus out. All right, we have our full antiderivative. On the next slide, we'll take this further, and we'll look at the bounds and plug them in and get an answer. So before we do that, I want to do some algebraic. I like to simplify as much as possible before I plug in. So if we distribute the 2 across, you see how we have the halves in both of them. Distributing the 2 makes those 2's go away. And then I see this x squared arctan x and this plus arctan x. Why should I keep them separate, you know? Let me put them together and factor out the arctan. I have x squared plus 1 quantity times arctan. A little easier, a little cleaner. And so we're ready to plug a 1 in now and get 2 arctan 1 minus 1. Ready to plug a 0 in and get the arctan of 0 minus 0. But, you know, arctan is 0, 0. So the lower limit's giving us all 0. And the arctan of 1, what angle do you plug into tangent and have it spit out a 1? That means the sine and cosine are the same. It's our familiar pi over 4. And so that's what we get. And at the end here, we just want to, you know, multiply by the 2 and get pi over 2. And then, I mean, this is a good answer. To get the answer that is given to you, what we're going to do is factor out a half. Now, both terms don't have a half. I understand that. What it does is it makes the inside end up looking a little cleaner algebraically. By factoring out a half, be careful with the 1, though. It's 1 is equal to a half times 2. So when you take out a half, you're left with the 2. And there we have it, pi over 2 times the quantity of pi minus 2. That's the version of our answer we'll go with. Okay, we had to sweat through that. It was integration by parts. We had a long divide. That was a little bit more than it should have been. Check out the other one, though. Remember how we square the outside, which is 1, and we square the tangent, which was the inside. It turns out that the tangent squared integral is pretty straightforward once you figure out what to do with it. There's an identity with tan squared. It is the fact that 1 plus the tangent squared on x is equal to the secant squared on x. I use x here, but, you know, we could put the y there for sure. And so we can solve for tan squared and get secant squared minus 1. Now watch what happens. It was minus the tan squared, so now it's minus the secant squared minus 1. Introduce some parentheses, distribute across the parentheses, and you end up with minus secant squared plus 1. So the 1 and the plus 1 double up to give you 2. We get the minus secant squared on y plus 1. And then we take this 1 and this 1, add them together, we get our 2. And we can definitely integrate secant squared. We know what function has secant squared as its derivative. And to integrate 2, we just get 2y. So it's not that bad. No integration by parts needed here. Ready to plug a pi over 4 in. Plug a 0 in. We get 2 pi over 4 minus tangent of pi over 4. Plug in 0, you get 0 again. And yeah, same answer, right? Tangent of pi over 4 is a 1. And you get pi over 2 minus that 1. And then we can do the same kind of thing, factor out the half. Or not. But to get a match, we'll do that and end up with pi over 2 times the quantity of pi minus 2. Okay? All right, great. Turns out the washer was the best way to go here.